In this lecture, we're going to actually switch gears completely and start talking about Laplace transforms. And so I'd like to say, if you've been following these lectures and you've been feeling confused lately, that's okay, because for the rest of the course, we're actually going to be talking about a completely different method for solving differential equations that doesn't rely on any of the methods we've talked about so far. So it's really going to use a completely different logic than any of the previous methods that we discussed. And it's a very important method in practice. So I would say this is actually probably the preferred method used by engineers when they come across a differential equation that they have to solve. So today we're going to define a Laplace transform, get used to using it, but we're actually not going to talk about differential equations at all. So let's define a Laplace transform first of all. So the Laplace transform, and we're actually going to use this symbol, kind of a curly L, to indicate a Laplace transform. And so it has an input and an output. So what is the input? The input is a function. Okay, so the Laplace transform of a function, and let's say that's a function of t, f of t. So it's defined to be, okay, I'm going to say what it is. So L of, and the input is a function of t, and what it is an integral, okay, from 0 to infinity. Okay, so it's an improper integral. Upper limit is infinity. And what is the function we're integrating? E to the negative st times our function f of t, dt. And that's all the Laplace transform is. Okay. Okay, so let's stare at this formula for a bit and make a few notes. Okay, so first thing to note is, well, what is the input and what is the output? So the input is a function of t, as we said. That's sort of what we mean by a transform. So the input is a function of the variable t. But what about the output? The output, do you see what we're going to get for the output? So the output is again a function, but it will not be a function of t because t is the variable of integration. So these are t values, actually, we're thinking of these as t values. And when we do this integral, we'll plug in these values. And so we will not have any t's left in this function. However, we'll have this variable s that appears in our answer. Okay. So the output will actually involve that variable s. So it will be a function of s, not of t. And so here's sort of the picture to have in mind. So we start with the function f of t, and then we're doing something to it. That's what we call L. And we get a function of s. So I'll write L of f of t, but you can see this is getting a little bit unwieldy, this notation. So actually, we will call this simply capital F of s. Okay, so when we use capital F of s, that's the Laplace transform of f of t, little f of t. Okay, what else do we note? So I mentioned that upper limit of infinity. So what does that mean? Let's just recall that. So you probably saw this in your integral calculus course. But yeah, what does this mean? Okay, so yeah, if we have, I'll just copy down this integral. If we have an upper limit of infinity, well, what does that actually mean? You can't actually plug in the number infinity. Infinity is not really a number. But what we mean is the limit of this integral, 0 to, let's say, b, as b goes to infinity. Okay? So that's what we mean by that upper limit of infinity. And I just want to say that, so this is all I'll talk about, this actually, but for some functions, f of t, this integral actually doesn't converge. Okay, meaning, you know, there could be an infinite amount of area under this curve. We're integrating from 0 to infinity. Okay, doesn't converge. And typically this happens for very fast growing functions. So here's an example. If f of t were the function e to the t squared, then if we plug that in for f of t, it turns out this integral does not converge. There's not a finite area under the curve. But all the functions we're going to be working with, the integral actually will converge, at least for some values of s. So this is all we'll talk about this issue. But yeah, let's dive right into it. Let's start calculating some Laplace transforms. Okay. So first example, let's do L of 1. Or actually, no, let's do L of 0. We'll call this example 0. L of 0, what is that? Plug in 0 for f of t. You're just integrating 0 from 0 to infinity, so that's 0. Okay. Now let's do example 1. So example 1 will be L of 1. Well, how do we do this? We'll just use this definition here. Okay, so this is the integral from 0 to infinity of e to the minus st times 1 dt. So it's just e to the negative st from 0 to infinity. Okay, what is this going to be? Well, let's first write this as a limit as b goes to infinity of the integral from 0 to b. And let's go ahead and do that integral. So we have the limit as b goes to infinity of, we have e to the negative st over s, right? And we have a negative sign that comes out. And we have to evaluate this integral at 0 and b. So I'll just make clear these are t values, right? It's easy to get confused and plug it in for the s instead. So these are t values. Okay, so that will look like this. We have minus e to the negative sb over s plus 1 over s, right? Plus because it's minus a negative. Okay, well, what do we have here? Well, this is actually a little bit subtle because we don't really know anything about s, right? S could be positive, it could be negative, it could be 0. If s is 0, then this is already not defined, so we have to be careful clearly. What if s is positive? Then you see how this exponential here, this number b is going to infinity. So this will be e to the very negative number, right? Something approaching negative infinity, which goes to 0. So this goes to 0. That's only if s is positive. If s is negative, this actually diverges. Okay. And what do we get? We're just left with this 1 over s. Okay, so just like we were talking about up here, we get a function of s as the answer. So the Laplace transform of 1 is 1 over s. And I just want to point out that this is only defined when s is positive. Otherwise, this is not the Laplace transform, right? Because we couldn't even do this integral if s were negative. Okay, let's do another example. Actually, let's just start right here. So example 2. What's the next easiest function? Well, let's do an exponential, e to the at. I think that actually works out being easier than something like t. Okay. Again, we just plug it into this definition here. We're going to be using this a lot today. Integral from 0 to infinity of e to the at times e to the minus st. So that's my f of t, e to the at dt. Okay, well, what do we get here? First thing I want to do is write this as a limit as b goes to infinity, 0 to b, and let's also simplify this expression a bit. So we have e to the minus st plus at dt. Now I need to grab a new sheet of paper. Okay, and then let's rewrite this so that we factor out the t. Let's actually factor out a negative sign too. So we have s minus a t dt. Okay. And this already feels a little bit familiar, right? What do we have here? We have the same integral here, except instead of s, we have s minus a. But s and s minus a are constants with respect to this integral, right? Don't get confused. S is a variable in the function that we're going to get at the end. But in this integral, it might as well be a constant, right? Because we're integrating with respect to t. So if we got 1 over s here, we should get 1 over s minus a. Because s has been replaced by s minus a. And this is defined when s minus a is greater than 0. Or in other words, when s is greater than a. Because this one was defined when this number here was greater than 0s. Okay. So the Laplace transform of e to the at ends up just being 1 over s minus a. So before we continue, I'd like to start recording some of these in a table. So we're going to be doing a lot of Laplace transforms over the coming lectures, and we don't want to basically be doing the same work over and over again, right? We already kind of noted here that we could save some time. Okay, so I have a book that I'm going to keep, and we have a table of Laplace transforms. We're going to start filling in this table. So what's the first one that we did? I guess 0 is not even worth putting in here, but let's do 1. What if f of t is the function 1? Well, our Laplace transform was 1 over s. And if f of t is the function e to the at, then our Laplace transform was 1 over s minus a. And for this course, at least, we're not going to care so much about the values of s where it's defined. Okay, so we'll keep that on the side. Let's do another one. So this we'll do, let's see, we're on example 3. This is a really important one. So this one actually has a name. It's called the exponential shift rule. Exponential shift rule. And this is the Laplace transform of an exponential e to the at times any function. Okay? So how do you do that? Turns out there's a really nice formula for it. So let's write our definition. We have e to the minus st times, here it's going to be e to the at times f of t dt. And this equals, so I'm not always going to put the limit as b goes to infinity I'll just write infinity. But when I do write infinity, we should remember that that doesn't actually mean plugging in the number infinity. It means taking a limit as that upper limit goes to infinity. Okay, so let's do this the same thing we did here. We'll rewrite this as e to the minus s minus a times t times f of t dt. And we're actually almost done already, because compare this right here to our definition of the Laplace transform. Looks exactly the same, except s is replaced by s minus a. Okay, that's the only difference. And s minus a is just a constant when it comes to this integral, because we're integrating with respect to t. So what is this? Well, let's use our convention of calling the Laplace transform of f of t capital F of s. So this is going to be capital F of, instead of s, I have s minus a. So it'll be capital F of s minus a. So in other words, to find this Laplace transform, all you have to do is find the Laplace transform of that function by itself. Okay? And then wherever you see an s, you replace it by s minus a. Okay, that's the exponential shift rule. Okay. And we've actually seen an example of that. So I just want to go back here. Actually, let's look at our table. Okay, you can think of e to the at as e to the at times 1. And then the exponential shift rule tells us you just need to take the Laplace transform of 1 and then replace the s by s minus a. Okay, so let's write the exponential shift rule in here next, because that's a really important one. Okay, so that's going to be capital F, where capital F is the Laplace transform of little f, but I need to replace all the s's I get with s minus a. Okay. I'll write here exponential shift rule. All right. So we're going to do some more calculations, but before we do, let's talk about an important property. So here's an important property of the Laplace transform. Okay. And so this is actually two properties. So I'll say number 1 and number 2. So number 1 is, if I have the Laplace transform of a sum, it turns out that I can just do the Laplace transform of both parts of that sum separately and then add them. Okay. And then the second property is, what if I have the Laplace transform of a constant times some function? Well, then I can just take that constant outside and multiply by the Laplace transform of the function itself. Okay? And I can actually combine these two. So 1 and 2 together. So in general, if I have the Laplace transform of something that looks like this, c1 times some function f plus c2 times some function g. That's going to be c1 times the Laplace transform of f plus c2 times the Laplace transform of g. And this is called linearity. You might have seen this before. So it's called linearity, combination of these two properties. And we say that the Laplace transform, the symbol L, is a linear operator. So it is a linear operator. Okay. Let's see why this property is true. It's actually very easy to show. So we'll start with this, and then we'll write down what that means. So we're just going to write down the definition. This one here. So it's integral from 0 to infinity, e to the minus st. Here's my function I'm plugging in, this whole thing. c1 f of t plus c2 g of t dt. Okay, but how do integrals work? So actually the integral itself is a linear operator, this integral sign, right? Because I can split this up. So I'll do it in 2 steps. Okay, plus the integral of e to the minus st c2 gt. Should have a dt. I'll turn that plus into a t. Okay, and then, of course, I can take constants outside of the integrals. So the linearity of the Laplace transform actually just comes from the linearity of the integral. Okay, and then this is c1. What is this right here? You want to get good at recognizing an integral as a Laplace transform of something. Right, so that's just the Laplace transform of f of t by itself. And then I have plus c2 times the Laplace transform of g of t. Okay, this is a super useful property. So let's do some examples using linearity. Okay, first one I want to do is a function that often comes up in differential equations. So this is example, where are we? We're example 4, I think. We'll do the Laplace transform of the so-called hyperbolic cosine. It's written cosine h of at, also pronounced cosh. Okay, and if you haven't seen these before, let's tell you what they are. So cosh of x is just defined to be e to the x plus e to the negative x over 2. And we can also do sine h, sinh of x, is e to the x minus e to the negative x over 2. And we give them these names, cosh and sinh, because these actually turn out to satisfy many properties that are analogous of sine and cosine. Okay, well, let's just do the Laplace transform. So even if you've seen these for the first time right now, this is still going to be very easy to do because we just copied down the definition. So e to the at plus e to the minus at over 2. These functions often come up when we're taking Laplace transforms also, so that's why I want to introduce them. Okay, and then let's use linearity. So we can take out that constant 1/2, and we can even split this up. We have e to the at plus L of e to the minus at. Right? That's by linearity. Okay, and let's just finish calculating this. So we have 1/2 times 1 over s minus a plus 1 over s plus a. Let's find a common denominator for these fractions. So the common denominator will be s minus a times s plus a. This one we have to multiply by s plus a over s plus a. This one we have to multiply by s minus a over s minus a. So we get this. But the a's cancel, and we get a 2s in the numerator. That cancels out with the 1/2. So we actually just get s over s squared minus a squared is our Laplace transform of the hyperbolic cosine. And then similarly, you can do the Laplace transform of the hyperbolic sine. And actually, I should mention, all of the examples in this lecture are ones that would be great to pause the video and try for yourself. They're all great practice. So if you'd like, you can pause the video, try to do this one on your own. but I'm going to write down what we get. So you should get a over s squared minus a squared. Looks very similar to that one. Okay. Well, what about the normal sine and cosine? And so there's another reason why I did the hyperbolic ones first. Okay, let's do cosine at. Okay. Well, one way to do it is to just plug it into this definition and do that integral. But that's actually a pretty difficult integral to do. I think we encountered this once before. And you have to do integration by parts twice, and it doesn't seem like it's going to work, but it actually does work. But the math gets very messy. So we're actually going to do this a different way, and that's with complex numbers. And so I actually want to point out something really cool. So let's recall Euler's formula. It's e to the I theta is cosine theta plus I sine theta. And sometimes it's kind of fun to just play around with this formula and see what you can do with it. So here's an example. So what if I put in a e to the I minus theta like that? So if I substitute minus theta for theta, let me do that on this side. Okay. And cosine of minus theta is just cosine of theta, because cosine is an even function. But sine of minus theta is minus sine of theta. So we get this actually. Okay. And now there's something really cool that you can do here. What if I add these two equations? So if I add these, here's what I get. I get e to the I theta plus e to the minus I theta on the left side. Now on the right side, I get 2 cosine theta. And then the I sine theta terms cancel. Right? So this tells me actually that cosine theta I can express in terms of these complex exponentials. Cosine of theta, where theta is a real number, right? I can express in terms of these complex functions. And look at how similar that formula looks to this one up here. Right? So that gives you some idea of how cosine and the hyperbolic cosine are related. Well, I can get a similar formula for sine. Can you see how I would do that? So instead of adding them, I can subtract. And then I get e to the I theta minus e to the negative I theta equals 2I, don't forget the I, sine theta. And so I get an interesting formula for sine theta, which is e to the I theta minus e to the minus I theta over 2I. Right? So that looks a little different than this one. There's an I in the numerator, or in the denominator. And so here's a crazy idea I'd like to use now. I'd like to use this formula to do cosine of at. Okay, just like we did for the hyperbolic cosine. So what do we get? We get e to the iat plus e to the minus iat over 2. Okay, and that is, by linearity, 1/2 of e to the Laplace transform of e to the iat plus the Laplace transform of e to the minus iat. Okay, and if we believe that this formula here, if we believe that this formula works for complex numbers, which it turns out it does, we get 1 over s minus ia, right? I'm just using our formula for the exponential, plus 1 over s plus ia. Okay, let's do the same thing. Just combine these over a common denominator. What is my denominator, by the way? It's s squared. The other two terms will cancel. The two cross terms will cancel, and then I get a plus a squared. S squared plus a squared. But this one I had to multiply by s plus ia. This one I had to multiply by s minus ia. And so I end up with s over s squared plus a squared. Right? Because the ia and the minus ia cancel. So that's really cool. We actually end up with a formula where all the i's disappear, and we just get s over s squared plus a squared. So again, very similar to that. It's actually very easy to get these confused, so you have to be really careful about that. And then here's a problem for you. So show that, this is a problem. Show that Laplace transform of the sine, t. Well, I can ask you to calculate it, but you probably already know what it's going to be, right? If we believe that there's some connection between the hyperbolic sine and the actual sine, it should be a over s squared plus a squared. But it's great practice to try to calculate that for yourself. It turns out to be a little bit harder than this one because of this I in the denominator. But the i's will eventually cancel, and we get this. So let's add all of these to our chart. Okay. So we've got cosine at and sine at, and then we'll do the hyperbolic ones also. I guess I did them in the reverse order in the lecture, but that's okay. So cosine is s over s squared plus a squared. So anytime we have the Laplace transform of cosine that we have to do, we don't have to do it out again. We can just look at this table. Sine is a over s squared plus a squared. No, remember, s is the variable here, and a is just this number that we start with. Okay. And for the hyperbolic trig functions, we get s squared minus a squared in the denominator. That's the only difference. Okay, great. So our table is really starting to shape up here. All right, I think we should do one more example. Let's do the Laplace transform of a polynomial. This is example, I didn't say which number it is. What are we on? We're example 6. Let's do L of a polynomial. Surely that will be an important one. Okay. And I just want to point out something. So we don't have to do a polynomial. It will suffice, actually, to actually just solve L of some power of t. And that's because a polynomial is just a sum of powers of t, possibly with coefficients. But by linearity, we can split that sum into all of its pieces and then take out the constants. So we only actually have to calculate things like this. So this is by linearity. Linearity. Okay, so let's try to do this one. This one's a little bit tricky, which is why I left it to the end. Okay. So we are going to do the Laplace transform of t to the n. So it's tricky, but it illustrates some important ideas. Okay, so we'll just use the definition. So e to the minus st. Hopefully you actually are starting to have this definition memorized by now. It's another reason I'm doing so many examples. So there's our definition. Make sure you also remember this minus sign up there, something that people will often forget. Okay. Well, let's think about how we're going to do this integral. Okay. So this is actually a typical calculus problem when you have an exponential function times a polynomial like this. How do you do that integral? And the way you do it is with integration by parts. So let's say what our integration by parts formula is. U dv equals, and let's actually put limits here. So uv minus integral of v du, but you have to evaluate this uv at the limits, okay? And when I say evaluate at infinity, we know what that means. So here's my integration by parts formula. Let's choose what u and v are in our example. Okay, so we have u, we have du, and we have v and dv. So again, my advice is to choose u to be something that becomes simpler when you take its derivative. So that looks like this one here we should choose to be u. Okay. So that's t to the n, which means du is n times t to the n minus 1 dt. Which means dv is the rest of it. And then we've already determined what v has to be. It's minus 1 over s e to the negative st. Okay, great. So actually don't need this integral symbol. Let's just use integration by parts, and we'll write down what we get. So we get minus 1 over s e to the minus st, t to the n, right? That's uv, evaluated at infinity and 0, minus this integral, right? v du. But we have minus and negative, so I'll be plus. Hope I have room here. We're going from 0 to infinity. Okay, let's be careful here. So we have a 1 over s e to the minus st, and then an n t to the n minus 1 dt. Okay. What is this first part going to be? Well, what happens as t goes to infinity? Remember, these are values of t, right? As t goes to infinity, this part's getting very large, right? But the exponential is going to 0, as long as s is positive. So if s is positive, this is going to 0, and the exponential always beats the polynomial. So the upper limit is 0, and what's the lower limit? Well, clearly 0, right? Because we have a t here. So we're plugging in 0 for t. So this whole first part is just going to go to 0. If s is positive. Okay. What is the second part going to be? Well, this looks like it's shaping up to be another integration by parts problem. But I'm actually not going to do integration by parts again. I'm just going to take out the constants. N over s is a constant in terms of this integral. And I have e to the minus st, t to the n minus 1 dt. Okay. Do you recognize what that integral is? It's n over s. This looks like the definition of Laplace transform, right? But there's my function that I'm taking the Laplace transform of, t to the n minus 1. So this is the Laplace transform of t to the n minus 1. Okay. So this is really cool. So what we just did is we showed that the Laplace transform of t to the n is n over s times the Laplace transform of t to the n minus 1. Okay. Similarly, so let's write that actually. Laplace transform of t to the n is n over s times the Laplace transform of t to the n minus 1. N minus 1. Similarly, what is the Laplace transform of t to the n minus 1? Can't we can just use the same formula, right? Instead of n, we have n minus 1. So you have n minus 1 over s times the Laplace transform of t to the n minus 2. Right? N minus 1 minus 1, which is n minus 2. And so we can just kind of unravel this. So the Laplace transform of t to the n is going to be n over s times Laplace transform of t to the n minus 1, which is n minus 1 over s, times the Laplace transform of t to the n minus 2, which is n minus 2 over s, times, etc., right? And will this ever terminate? So will this ever end? Well, it will when n when this numerator becomes 1, let's say. Then we just get 1 over s. And then we have times the Laplace transform of 1 less is t to the 0, but t to the 0 is just 1, right? So this bit here is just 1 over s, right? That was our first formula ever. Laplace transform of 1 is just 1 over s. Okay, so let's take stock here. What do we have here? How many terms do we have? How many factors do we have? We have n terms, right? N all the way down to 1, times this extra 1 here. And so what is our formula going to be? It's going to be n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1, right? Also known as n factorial. Right? N factorial over, how many s's do we have? We have n there, but we have 1 extra there. So it's n factorial over s to the n plus 1. Right? Okay. But we should be careful here. How do we know we're going to get down to 1 eventually? Well, that will always be true as long as n is a positive integer. But what if n was something like 5.2? This would be 4.2, 3.2, 2.2, 1.2, 0.2. We wouldn't ever be able to get down to 1 and then to 0. So this only works, this warning, this formula only works if n is a positive integer. And so it turns out if you want a formula that works even when it's not a positive integer, you need something that generalizes this factorial function. And that something is called a gamma function, but we're not going to talk about the gamma function in this class at least. But you can actually have a formula for t to the n where n is any positive number. Okay. Let's record that formula. So I should write in here n is greater than 0 and an integer. And our formula is n factorial over s to the n plus 1. And so you can use this one to take the Laplace transform of a polynomial. Okay. I'd just like to give you a quick problem. So here's a problem. So let's suppose you're given that the Laplace transform of 1 over the square root of t is this, square root of pi over s. Okay. I want you to actually use this knowledge to find the Laplace transform of the square root of t. Okay. So this is kind of a tricky problem, but what you're going to do is the exact same method that we did here. So this is t to the 1/2. Okay. So see if you can write t to the 1/2, use integration by parts, and you'll get something that looks like this in the integral. And so you'll actually be able to write this in terms of this given Laplace transform. Okay. And if you're curious, the square root of pi is actually coming from a special value of this gamma function that I was talking about. But you don't need a gamma function in order to do this problem. Okay. I think that's probably enough examples for now. But what I want to do is just record a few more useful formulas. And so often what we're going to want to do is take the Laplace transform of something that looks like an exponential times a trig function. E to the AT times cosine BT. I mean, we've seen these come up a lot in our second order, when we were studying second order differential equations. And e to the AT times sine BT. And then even, let's say we have t to the n times e to the AT. In this case, I need the same disclaimer, I think. N is a positive integer. Okay. Well, we don't need anything new to do this. See if you can actually come up with these three, just from what we have in this table so far. And in particular, this is going to be the way to get these formulas. So what is this saying? It's saying if we want to take the Laplace transform of an exponential times a cosine, all we have to do is take the Laplace transform of the cosine, right? And then plug in s minus a wherever we see an s. So let's try that. So I'm just going to write down the Laplace transform of the cosine. Here I have to be careful because it's cosine bt instead of cosine at, right? So that a is actually a b. Okay, but then whenever I see an s, I'm replacing it with s minus a. So I have s minus a over s minus a squared plus b squared. Okay. And then we do the same thing with the sign. Here, yeah, instead of the a, I have a b. Right, so I have b over s squared plus b squared, but the s I need to replace with s minus a by the exponential shift rule. So exponential shift rule is a bit tricky to use, but hopefully you're getting the hang of it. How would I do this one? Again, I have an exponential times something I know the Laplace transform of, right? So I'm just going to copy that down. It's n factorial over, but what do I have to do here? I have to replace the s with s minus a, that number up there in the exponential, right? S minus a to the n plus 1. Okay. Finally, I just want to give you another useful formula that we may or may not use, but often comes up when we're applying this to differential equations. It's sort of a version of the exponential shift rule, but instead of multiplication by an exponential, we're multiplying by a polynomial. Again, we want n to be a positive integer. And so it turns out, I'm not going to derive this formula today because this lecture is already getting a bit long, but we have negative 1 to the n times capital F of s, but you take the nth derivative. Okay? So this notation means nth derivative. Okay? So for example, if you have t times cosine at, what this is saying to do is you need to multiply, so here t, it would be t to the 1, and so I need to multiply by a negative 1, right? Negative 1 to the 1 is negative 1. And then I need to take the nth derivative of that formula right there, right? Because this is the Laplace transform of my cosine. But I need to take the nth derivative of this, which n is 1 here, so I just need to take the first derivative of that. And that will be the Laplace transform that I get. Okay, so this is our table so far, and in the next lecture we will talk about how to essentially go the other way. So if we know the Laplace transform of a function, how do we figure out what the function was that we started with? And that's called taking an inverse Laplace transform. And then after that we will finally talk about how this can be used to solve differential equations.